What's up, fellas? Last week we examined the economic viability of producing aluminum oxide on a DIY basis. We were using electrolysis because there's very little information on the subject of producing aluminum oxide via electrolysis, so I decided to fill that gap and I wanted to check it out for myself. I didn't want to buy chemicals and mess with none of that stuff. I just wanted to try it with electrolysis and aluminum. So that's the mess we've got here. And we left some unfinished business. So in this video, we calcined the aluminum oxide to the appropriate temperatures because a lot of the other videos are showing you the wrong way of doing it. They're showing you beta aluminum oxide, which is an unstable form. This right here would be the alpha aluminum oxide, which is the most stable and the hardest form of aluminum oxide you can get. It's like a 9 on the Mohs scale. So here's the electrolysis cell that we examined, and I gotta say, man, it works, but it's a waste of time and money. You can buy a pound of this stuff for $6 online from a pottery store. So let's check this out. So in conclusion, the best way to make aluminum oxide is with a credit card. I don't recommend you use your debit card online ever. Never do that. So yeah, 55-pound bag. I don't know what that costs. They're looking at $6 for a pound, maybe. Man, maybe we should make our own. Hold on a minute. That's pretty steep, dude. I mean, 1 pound ain't all that much either. So here's the cell that we looked at in that last video, and I just want to thank you guys that came to the rescue in the comment section and revealed so much information, a lot of valuable information, and I do appreciate your comments. Alright, so I did this video because there's a lot of confusion online. There's chemists showing people how to make aluminum oxide by calcining it to 500 degrees or whatever your little oven will do. And this stuff did hit 500 degrees, but the truth is, anything that has not been heated to at least 1200 degrees is called boehmite. And it's a beta form of aluminum oxide, and it will absorb moisture from the air. You can't even get an accurate measurement of the weight because it's continually absorbing moisture. Now, when you go above 1200 degrees, you get the alpha aluminum oxide, and it is a very stable form, and that's around 2192 degrees Fahrenheit that you got to get it. I was referring to 1200 C, I think. And this is the stuff that sapphires and rubies and topaz and emeralds are made out of, but they have small trace contaminations. So the information on YouTube was not sufficient for my studies in refractories. I needed the alpha grade aluminum oxide that is used for, refractories and in pottery and stuff like that. But they were kind of sending me down the wrong path, so I had to do my own research and dig in a little bit deeper. So if you make aluminum oxide and you bring it up to 500 degrees Fahrenheit, it's going to start absorbing moisture. That's what they make the aluminum oxide desiccant beads out of, is the beta form, not the high grade refractory alpha form that has to be heated to extremely high temperature. So I kind of got sent down on a duck mission there, a little disappointed. But it's my fault for, listening to amateurs. And I'm not insulting anybody. It's just YouTube is dangerous, man. It's dangerous. This is how much I got off that first batch. And like an idiot, I pulverized it into a powder and then put it in a crucible. And I think most of it blew away because you've seen how little we got of the brown stuff. Wasn't a whole lot. And the conclusion is, it's a waste of time to make your own aluminum oxide. I don't recommend you bother with it. Don't go buy chemicals. If you can go out and buy a bottle of muriatic acid, which is the best way, then you've got money to buy some high quality stuff online. You might as well just buy it from a pottery place. If you buy it anywhere else from a pottery supply company, you're going to get ripped off big time. So just keep that in mind. All right, fellas, so here's the brass tacks. I'm very grateful for the inputs you guys provided on that last video. We had like 70 comments in 2 days. A lot of it was about my ranting, but for the most part, there was some really good chemistry comments. And the conclusion I'm drawing, yes, a 55-pound bag of alpha aluminum oxide costs about 350 bucks, which is pretty steep. But the hours and time that you would put into making it and calcining it on your own don't justify the effort. Unless you're making this stuff by the ton, you're not going to beat their price. Your time's more valuable than that, I assure you. Ain't no way I'm working for $6 an hour, dude. And there's no way I can produce a pound in an hour. So it's a waste of time to make my own. I just had to try it out. I was hard up. I didn't have the cash to buy some, so I thought I'd give it a shot. But in conclusion, it can be done with electrolysis. So if you've got a wild hair and you insist and you must, then yes, it can be done with electrolysis with salt water. Very small amount of salt water. And energy density plays a role in how pure the material is going to be. The higher the energy density, how many amps per square inch, is going to produce a very contaminated solution with aluminum particles. If you go above like 3 amps on a 10 square inch surface, you're going to start producing a lot of aluminum particles and you'll get a gray material, which isn't the end of the world if you're going to calcine it anyway. But a quick note on calcination. Simply bringing the material up to 1200 degrees Celsius does not constitute calcination. It is a crystalline material. You are growing crystals in a high temperature, like your own volcano. And these crystals take time to grow. And some of my testing previously done on calcining calcium, or just rocks out of the driveway to make calcium oxide, showed that there was a drastic difference in reactivity between a 1 hour calcination and a 2.5 hour calcination. I could put 10 grams in a cup of water with the 1 hour and it would raise the temperature to 100 degrees. I could put that same 10 grams of the 2.5 hour stuff in a cup of water and it would raise the temperature to 210 degrees, like almost boiling the water. So that's a good way to gauge, the calcination progress. So I left this stuff in the furnace for about an hour. Like an idiot, I pulverized it prior to putting it in the crucible. I should have just left it in chunk form. The little felt pad that we put on top of it to keep it from blowing away melted. It's not really aluminosilicate fiber. It's some other type of ceramic fiber. I thought it was aluminosilicate fiber, which would have held up to those temperatures, but this stuff just melted into a little piece of quartz, basically. So there was some other type of mineral wool, and I wasted 8 liters of oil. The oil was free, but I could have done a lot more valuable stuff with it. I did use a little bit of gas for the air compressor. We were running at 150 kilowatts of energy for about an hour and 15 minutes. And we were running at white hot temperatures. The hotter the better for this process. So we were at 2,650 degrees Fahrenheit approximately, which is a glowing white hot color on the temperature scale. And I will never do this again. There is no way, no how. I had this cell running for days. I put all this research in. I tried this and that. I changed the energy densities here and there. And yes, you can produce some fairly good volumes of aluminum oxide, the beta form. I don't know for sure that all my aluminum oxide blew away. It may not have. And if it didn't, you've seen we only got 69 grams, I think. No, it was less than that. I don't even think I bothered weighing it. We got about this much in a cup and we started off with that much. So, not my idea of a viable process at all. I'll never do it again. And I tried using the beta material to make some refractories, and it's a total flop. But the aluminum contamination causes bubbling. You're producing hydrogen gas as soon as it comes in contact with the potassium silicate. So it's a no-go. It cannot be used in that form. You cannot heat aluminum hydroxide to 500 degrees and then call that aluminum oxide, in my opinion. At least not the kind I was looking for. And I don't think anybody else wants to use that stuff because it absorbs water. It absorbs water so quickly that the scientists complain of their inability to weigh the material to determine their yield in their process. So the best way of making this stuff, from what I can tell in my research, would be muriatic acid, because the end products are not as toxic, and you're not running an electrolysis cell for days on end. You can make a pretty good large amount. Using sodium hydroxide produces a substance called sodium aluminate, which is highly soluble in water. So you're getting this very caustic material that you then have to pump carbon dioxide gas through it to produce sodium carbonate and aluminum hydroxide, which why would you do that unless you're stranded somewhere in Mexico and you can't get the stuff shipped to you? That's the only reason you would ever want to do this. If you like electrolysis, and I understand that, I started my YouTube as an electrolysis buff. I was an HHO warrior. I was out there to tell the world that HHO is a fraud and a scam, because I saw all these videos lying about HHO can save you gas mileage on your car. And I love electrolysis. I have a massive electrolysis cell right here. This is a 10,000 watt bipolar cell electrolyzer. So really cool stuff. I use this for a hydrogen torch, oxyhydrogen torch, for brazing and things like that. It's just kind of cool. I sometimes do gas modification with it, where I add propane with that gas and make a very special flame. But that's neither here nor there. I just kind of wanted to follow up. I left you guys hanging with an unfinished video. We never actually calcined the material that I made through the electrolysis process. Oh man, I'm running out of air. And I just wanted to thank everybody for the vast wealth of information. A lot of chemists came online to save the day and share a lot of things. So from now on, when someone goes to look up, can you produce aluminum oxide via electrolysis, there's going to be a lot of information available. Because I found a desert. There's one guy with one video, and he didn't do so hot. So, and the other videos, I guess these guys are making rubies and microwaves or whatever. They're not giving you the full story. I don't want to beat them to death, but totally inadequate for me. They sent me down a bad road, and you know, there was a bridge across a river right down the way, and they told me to walk through the water, and that's just not good for research. So that video and this video are to kind of patch up that hole. So anyone comes looking for it, I'm telling you, don't do it. Don't bother, man. For $12, you can have 2 pounds. It would take you a week to make 2 pounds of this stuff with electrolysis. So, like, how valuable is your time? You know, if you're dead broke, and that's very understandable this day and age, and you have the equipment available to do an electrolysis process, then maybe it's justified. But not only will I never do it again, I didn't even produce enough of the stuff I needed to do the geopolymer testing that I'm involved in. I'm working on refractories, adhesives, coatings, and refractory materials in itself. Mostly the adhesives and the coatings are what I'm focusing on, what I'm interested in. And I've got everything ready, except for I don't have any aluminum oxide. So I had to do a lot of studying to bring this thing home. Sometimes you got to be an expert at stuff. You got to teach yourself to be an expert. That's kind of what I went through this week. I took a 1-week college course on aluminum oxide for you guys, and just kind of paying it forward by posting this information. If this is something you want to do, the electrolysis is cleaner than the chemical processes. It's safer. It is doable. You can get pretty large quantities of material, and maybe I'll bore some of you to death with showing some more clips of that in this video. There's some other stuff in this video, but it was such a failure. It's like, why am I bothering to post this? So if you want to see how not to do it, you know, you can keep watching this video. There's some cool stuff to look at, but I think you need to turn this video off and just get the hell out of here. You've got better things to do than watch me fail. This metal air stone was reacting with the mixture. It was acting as a passive plate, like a dry plate cell. And a dry plate cell, you don't need to have it connected to electricity for it to undergo electrolysis. Let me show you what I mean. This monster right here is a massive dry plate cell. And I forget what they're called, man. It's been so long since I've messed with this stuff. The only thing connected electrically is this plate, the end plate, and this end plate. All the rest of them are not mechanically connected to the electricity. The electrolyte itself acts like the electrical connector. I think they're called neutral plates, maybe. I can't remember the term. It's been so long, it's been like 5 years. But that's kind of what's happening to my air stone. It's acting like one of these inner neutral plates. And you've got a positive and a negative here. Massive DC electrolyzer. This thing can do 20,000 watts easy if you got that much electricity to hook up to it. It's a pretty big unit. This is an electrolysis cell. And it's made for the purpose of an oxyhydrogen torch at this point. I think that's what was happening, is this was acting like a neutral plate and possibly contaminating my solution with some chromium. I doubt there's any hexavalent chromium in there. The energy level to produce that's very high, but nonetheless, not an ideal scenario. So we're done with the air stone for now. I'm just gonna do this. So this was a very valuable discovery. I noticed, let me get a light on this for you. You can see, plain as day, there's a transition. And what happened? Why did we go from this light color, beautiful looking aluminum hydroxide to this frothy mess? This stuff here is thick, heavy powder. I moved the cathode closer to the anode, and that increased the energy density. What do I mean by energy density? That's watts per square inch. If the wattage per square inch is too high, or the amperage, whatever you want, amperage would be more suitable, then you run into problems. We were producing this nice white buildup here. And then we started doing the gray. So I don't know if I can vacuum that out of there or not.
It there for water, and the people murmured against Moses. Good at murmuring, aren't they? First, how many times did they bring Egypt into the story? How many would you like to go back to the life that you lived before God saved you? You ever think about that?
All right, so I don't know what the heck's going on, guys. We were running one way the other day, and now I can't replicate that activity. So I decided to screw it. I threw about another 5-10 grams of salt in there. Brought the energy density up to that. So we're just gonna jam out some gray sludge. They say this gray sludge is aluminum hydroxide. Maybe it has some aluminum contamination in there. Some nanoparticles. We are getting a white precipitate. A lot of people in the last video said that there's no way you can make sodium aluminate in this, which is good news. And I also learned that sodium aluminate is highly soluble in water. So any solid that we are seeing is most likely not sodium aluminate, which is good. Trying this out a little better. All right, I just pulled this batch off the pellet stove. It was a little bit hotter than this. It's cooled off some. All right, so aluminum oxide does not require additional oxygen from the atmosphere to calcine. So to keep from losing all that powder, I'm gonna put this felt baffle in place. This is aluminosilicate insulation. I'm gonna put this crucible lid in place so that we don't lose it all. And we'll calcine it in the morning. Okay, crucible in place. Okay, so not ideal. I don't know if we'll be able to get all that out of there once it gets cooled off all the way. Pretty hard stuff. I can't crush that with my fingers. It breaks up, but it's very tough. Suppose a lot of it possibly blew away. A couple little pieces of that white crap in there. Okay, so here's the pH of that solution. It's certainly not a 10. Maybe a 9. So that definitely removes the possibility of there being any sodium hydroxide or sodium aluminate. Sodium aluminate is a highly caustic solution with a pH of 12. So that's good to see. We have two different phases here. This is 1.6 amps and this is about 3.4 amps. So we're looking at the corresponding energy densities. And it would appear that the lower the energy density, the less aluminum contamination you get. This stuff's still kind of wet. I guess it feels like it. Maybe not. So I'm definitely not going to grind this stuff up before I calcine it this time. Probably better to leave it in chunk form so it's not all just blowing out of the crucible on me. So this is the alpha phase aluminum oxide. It's very hard stuff. It's going to need pulverized to be used. A little bit of contamination in there from melted crucible. So if you guys got any input on that, here's this stuff. This is also aluminum hydroxide, but this is also aluminum oxide. Now that it's been heated to 500 degrees, but it's a different phase. This is the gamma, and it's an unstable phase because it will turn into this. If we were to put this into a refractory and try and do something with it, it would turn into this stuff on us. So that's why they say it's an unstable phase, and it's used for low temperature catalysts and stuff like that. This is the stuff that's used for high temperature catalyst. Yeah, I'm definitely sticking with 8.5 on that. So that's good to know. We don't have any sodium aluminate, so you guys in the comments on that last video were 100% correct. I applaud you. I don't want to touch this electrode. Here's our lead electrode. Set that to the side. And here is the aluminum anode. Just pretty caked with stuff. Let that thing dry off. We'll let it dry off and we'll have a look. This is where a lot of that coloring is coming from. As you can see, it's a finely divided material, which is likely like the magnesium or whatever alloy was in this stuff. So Pretty messy stuff. And all over the top of this, we've got some fairly white, pure material there, which we'll harvest later. But yeah, lower energy density definitely gives you less aluminum contamination. All right, fellas, so that's my 2 cents. I put a lot of research into this, man, and the conclusion is don't do it. It's just not economical at all. You're wasting time that you're never going to get back. $6 a pound? Like, why would you waste your life away producing this material when it can be had for $6 a pound? And I'm making it at cocaine prices. It's like, what the heck, dude? It's just not doable. So, $6 to $10 a pound from a pottery shop. I don't know if I can beat that.